Alrighty, friends, so work day, but let's talk about a few things because this is the hardest homework of the semester. I don't know if you've noticed. If you haven't noticed, I probably don't want to know because it means you haven't started on it. Because this shit is hard. So let's talk a little bit about some strategies for getting through this. At least two of the problems can be done if you think back to the proof I did last Wednesday. And I want to just reiterate the construction. And I think it'll make sense. And Christian agreed. Christian came in to talk to me about these. He's like, oh yeah, that helps, right? Is that, yeah.
Yeah, the second time.
The second time, the second time, yeah. So let's just really talk about that construction. Why am I doing that? I don't want to plane. I just want to circle. So let's start with the unit disk. So that's unit disk. There's 0, there's 1. And the construction was this. We want to find two clines to invert over that send a point P to 0 and a point Q that's already on the boundary to 1. That's our goal. We just want a thing that does that. You have a problem that's very much like this. I forget which one it was. Problem, let me just tell you. So you can definitely use this for the first problem to prove that the geometry is homogeneous. And we'll talk about that in just a minute too. But, oh my goodness, where's that problem? This is problem 4 is basically exactly what we're about to do. It's just a little bit more general. But this is how you do problem 4. So, step 1, so that's the setup. Let me get my disk back. That's okay. I've seen some serious potatoes drawn for this. This is not bad. Still, whatever. So there's 0, and here's my point P. So first what we do is we get P onto 0. What that's going to do is it's going to move Q, but it's going to move Q to somewhere else on the boundary. So that's okay. We'll take care of Q with a rotation. So step 1 is just get P mapped onto 0 and figure out what do you got to reflect across for it to land there. So the first thing we do, as we often do in this class, is we construct the symmetric partner, the reflection of P across the unit circle. Does that make sense, what I'm saying there? That's, if you take P and you invert it, you get P star. So P star equals the inversion of P in the unit circle. That symbol, way too complicated symbol, way too fancy looking, but that's just the unit circle. It's also our infinity. So it's one of our infinities. I want to point something out here, and I think it's one of the most confusing things about all of this, is that this becomes our world, this little disk, and this edge, this circle becomes infinity in our little world. But there's actually a much bigger world that it all lives in that we can refer to. For example, this P star is going to land outside of our world. But we just accept it and it's okay. And there's like a whole other infinity as well, right? There's another infinity. If I invert 0 around this circle, it goes to the other infinity. So there's a lot of weird things coming on. It's kind of this dichotomy that we just have to become comfortable with and just stop questioning and just, just work with it. Because it's weird shit. So, what I want to do is first just note that P star is an easy thing to produce. So here, maybe let me go through this. Find P star, and P star is that guy. And inversions always live on a line between the point you're inverting and the center of the circle you're inverting around. Okay. We know this, we know that. And we know a lot of things, we just forget them, right? And sometimes you're not sure how to put it all together. The other thing I was talking to Christian about, and Lou, is that this assignment suddenly, I feel like we went like the bottom of the ocean dropped out a little bit. And the analogy that I came up with talking to those guys was that we've basically spent the last whatever weeks doing like a wilderness survival course in a classroom, and then we got dropped in the wilderness without a flint and a compass, and we just have to freaking figure out the basics. Like, what do I do? Oh my God, you start panicking, but you got it all. We just have to figure out how to put it together. So let's make fire. This is how you make fire right here. So find the inversion of P. Awesome. Next step, and I'm using colors because man, I miss having that app that we messed with. That thing is so sweet. What I'm going to do next is create a circle whose diameter is 0 P star. Yeah. Tater. Make that tater that goes through 0 and P star. So 2, create circle C with diameter 0 P star. We'll call that C1. No, we'll just call it C because I think we're going to have C1 in a minute. So this critter is C. And I hate how he looks. Just have to fix it a little bit. That's a little better. So there's C. Next step. Note where it intersects S1 infinity. So where does it intersect the boundary of our world? And you can pick either point. So I'm going to pick that point right there and call that, well, I don't want to call it Q. How about we just call it R right there. So 3. Choose one of the 2 intersections of S1 infinity and this circle from 2, C. Label that all. Label it R. Cool. Now we got one more thing to do. Well, 2 more things. The biggest one is we're going to create another circle now. And we need a new color, green. I'm going to create now a circle with P stars in center. Oh, what can I help you with there, Morgan? What's hard to see?
2 intersections?
Yes. So when I do this.
Yeah, I wasn't sure if it was
okay.
Intersections or not.
Yeah, I can see why. That makes sense to me. Yeah. You're out in the wilderness. You're like, who wrote these goddamn survival instructions? And does that say eat the stone or use the stone? Okay. So next step 4, is create a circle with center P star and radius R. Radius P star R. So 4, I guess this is going to be green. Create a circle, and this is going to be our circle that we really want. A circle C1 with radius P star R. So that point of intersection, that's going to be a point on your circle. And I just drew the radius right there, but I'm going to actually want to keep it. And then so I create a circle, and it'll go through, if things go well, it'll go through the other intersection as well. So that's going to be C1, and that's the circle we want. That's the circle that's going to move P to 0, but we have to prove that that's going to be the case and convince ourselves. And if you follow this, no matter how bizarre it is, you've really understood something. This is a fundamental construction. So let me just make sure everybody's with me. Is there anything that needs clarification at all? Okay. So that's circle C1. Now, we want to, the claim is this. Claim that if we invert about C1, P gets sent to 0. That's what we're going to show. So how do we show that? Well, we wish we had more colors. And we do, I guess. Cool. So to see that, you're going to create a right triangle. What I want to show, where I'm headed, is I want to show that this circle and the green circle, my original disk and this green circle, are at right angles to each other. So I want to show the intersection at R is a right angle. And to do that, I create a triangle in here. So I'm going to create the triangle P, good God, PR0. And then it's got hypotenuse like that. So step 5 is note that the triangle 0 P star R is inscribed in half a circle. So let's actually draw that. What do I mean by that? That triangle, so there's the edge, this is P star, this is 0, and then I have this point R over here, that guy like that sits inside this circle C. So this was actually the circle C. Tell me if that's making sense. And if okay, cool. We have to go to this basic geometry fact that any such triangle that has its hypotenuse as the diameter of a circle and a point on the circle is a right triangle. That's like some, and I keep saying basic geometry stuff, because it doesn't seem very basic, but it's Euclidean geometry. So it's the Euclidean geometry fact. So note that the circle in the half circle is a right triangle. And that is like that's some Euclid shit. So, does that sound good? Yeah? Euclid. Praise Euclid. All right. So that means this is a right angle. Cool. So now I actually see that the blue circle, and because this line is tangent to the black circle, and this red line here is the radius, this is the tangent line to the black circle, and it also intersects this blue circle. So, wait, what? Wait, what? I've done this so many times. Christian, didn't we have this conversation just a little bit ago?
What is P star and N, like that line segment, and is tangent to the black circle, and then N to O, that line segment, is tangent to the green circle?
Oh, it's the, oh, right, okay, yeah, I was looking at the wrong circle. It's not the blue circle.
Yeah.
Whew, got scared, okay. So this, let's get rid of this blue circle, because that actually, we're done with it. Whew, got myself confused. So easy to do. Cool. Yes, the green circle, which was really hard to see. That's why I forgot it. So now you see that you have two tangents. You have the tangent to the black circle here, and then the tangent to the green circle here, and they meet at a right angle. And so those two things intersect at a right angle. So let me write that up. Since R is a point of tangency to C and S1 infinity, those two circles are orthogonal. I'm going to use my symbol for orthogonal. Okay. Let me stop. Tell me if that.
I think it's C1, right? The green circle?
Thank you. Yes, thank you. Yes, sir. C1. If we got this, we're good to go. Because when two circles intersect at a right angle, and I invert around either one, if I invert the other circle around either of the other circles, they just turn back on themselves. So if you invert, you got a circle, and you have another circle that's orthogonal to it, and you invert around this first circle, these two don't change. They remain the same, like this. The points flip, but it looks the same. It just maps back on itself. And then similarly for the other one. So if I flip around this one flips, but back onto itself. And we actually saw this on Monday when we were playing, I believe. Freaking positive that that happened. So that means, okay, where am I going? What the heck am I doing? Awesome, okay, I think I got it. So we're good to go. So let's actually make that note. So thus, yeah, that red. Thus, if we invert C1, if we invert about C1, the unit circle maps back on it to itself. Because they are orthogonal circles. So I'm going to invert around this C. And then this side here of the triangle is going to turn into this side. And this little arc in here turns into the rest of the circle, outside of the green circle. But more importantly, this means that P star, where does P star go when I invert around the green circle? P star is its center. Where does the center of a circle go when you invert around it? Infinity, yeah, beautiful. P star goes to infinity. The center of the circle goes to infinity. Center goes to infinity. Because you end up dividing by that, essentially. You divide by the distance to that. So, this is going to get us that P goes to 0. And why is that? So, can somebody actually tell us? This implies that P goes to 0. Why? Can somebody tell us why? I know a couple folks who can. I know one folk who definitely we had the conversation. Why is that? What do you know about symmetric points and inversion? They stay symmetric. Beautiful. So if I have a pair of symmetric points and I invert them both around a circle, they stay symmetric. So because symmetric points are preserved under inversion. And the symmetric partner to infinity is 0. So if these two are symmetric, and one of them goes to infinity, the other one has to go to the symmetric partner of infinity, which is 0. So since P star goes to infinity, P goes to the symmetric partner. I'm going to write this out. Symmetric partner of infinity, which is 0. So that's a crazy ass way to get there, but that gets us there. It's not something you can look at and see. You cannot, there's no way to look at this and go, well, of course P would go there. We have to get at it in this weird backdoor way, knowing that that goes to infinity, so therefore that goes there. Okay, so I got one last thing to show you then. I hope this is making a little bit more sense than it did on Wednesday. Just like 10% is enough. We just need a tiny wafer thin increase in our understanding of this. So let's look at, so after inverting about the C1 that we built, we have this situation. We had this point, so actually over here, trying to think, how do we get the 1? We had another point in there. Did I say we had another point on here, Q, at the beginning? Did that happen today? Okay, because like sometimes, yeah, okay. So we had this point Q out here. We had this point P and we had a point Q. Our goal was to send P to 0 and Q to 1. Your goal, the goal you have to do in our problem, is your Q is not on the boundary. Once you're on the boundary, you stay on the boundary with all the stuff we do, all the Mobius transforms, all the inversions. Boundary points can't leave the boundary. That's infinity. It's a place you can't get to. It's like the speed of light. Maybe you can travel there, you can get there, but you can't approach it. You can't get there by approaching it anyway. So I don't know, that's maybe complete garbage, what I just said. But I send P to 0, I want to send Q to 1. So what happened is we just flipped this thing over that green circle, so Q got flipped as well. And where did Q get flipped? On somewhere on this line. Oh wait, yeah. Oh wait, our Q was on the boundary, right? So let's say Q was down here. Let's say our Q was here. We flipped to this place because it stays on the boundary and inversion happens on lines through the center of inversion. So I know that Q star had to be somewhere like that if it was here. If it had been, I think I had originally had it like right here. If it had been here, then it would have gone to right there. The key thing is that that point that was on the boundary got moved somewhere. So let's just say it's here. So Q star, or Q prime, equals image of Q after inversion in C1. And we've already got 0 here, and that would, you know, P, that's actually where P got sent, so we're all good. That way, that is not a center. That ain't a center. I don't like it. I can't make it. It's a little bit better. 0. That's where P got sent. Okay, so friends, all we have to do now is get Q to 1. That's our goal. Q prime to 1. So the way we do that is we notice that there's an angle here, like this. And this angle is theta, we don't know what it is, but we bisect that angle. So I find the bisector, which is a straight line. So this is the straight line, truly a straight line, not some weird ass hyperbolic straight line or something like that. Not a cline, a freaking line. Straight line bisector of Q prime 0, 1. That's a triangle, or an angle, just an angle. Q prime 0, 1. Take the bisector of that. So get the straight line bisector of that angle and invert over that. And I think do you think I should talk about this, Christian? Because it helped you when I was talking about inversion over lines.
Like just the fact that, yeah, sure, why not?
Okay, I like that. So we're going to reflect over this line L, straight line bisector of that. Reflection over a line is just inversion around a circle that contains infinity. Because if you think about the Riemann sphere, here's infinity, here's 0 down here. I've got a line through 0. That's just a giant circle on the Riemann sphere that goes through 0 and infinity. When I flip around it, it's just inversion. It's just like a beautifully symmetric inversion. When you flip around a circle And you take that point and flip it, it goes way out. And you take that point there, it stays close. But when you invert around the line, because its center is a million miles away, infinitely miles away, this just acts symmetrically. So reflection around the line is inversion around a climb. So that's C2. We'll call it L. So our final transformation is step 1, reflect over C1, and then 2, reflect over this L. And reflect is just invert. And so the composition of those two is the thing that does what we want. That will then send this Q to 1. Now you might be saying to yourself, well, wait a minute, didn't we move this? We did not, because we rotated, which fixes 0 and infinity. So rotations just leave that 0 fixed. So we didn't move it, huzzah. So our final transformation is T equals inversion over L composed with inversion over C1. In that order. Do that first, then that. Lordy. Your problem, whatever it was I said it was. Which one was it? 4, yeah. Your problem 4, just argue the same thing. The good news for you is that, well, I don't even know if it's good news, it's just different news. Your original Q was inside the disk. So after this flip here, do the same flip here. Your Q won't be on the boundary, it'll just be somewhere in here. And that's okay. Still do the same thing. Find its angle, cut it in half, reflect over that, and you'll just move it over to the real axis. That's why they say the real axis, because you'll land somewhere on there. You don't have to tell where. It's just that you will. You have to. Okay. I don't know how much work time we're going to have because I have more shit to tell you. But we'll keep it. Is there any questions on this? Because I definitely want to give you another hint. This actually knocks out problem 1 as well about the homogeneity. And let me explain why. So we can create a Mobius transformation, right? This is a Mobius transformation. It's an even number of inversions. So we just created a P that sent, a T that sent some arbitrary P to 0. We could create another one in the same way that sent some point Q to 0. Okay, who gives a shit about P star and 1? We don't care. We don't care about anything else. We know that we can create a T that sends P to 0, and we can do a different one that sends a different point Q to 0. So we got a P, and we got a Q. And we send them both to 0. This is T, and then S does the same thing. How could I send P to Q using those two? What do we have to do? I don't want the person we already talked to about this to tell us. How could we use these two things, these two invertible transformations? Do you know? Do you know, Ms. Kitra?
Well, I'm assuming we would take the inverse of one of them.
I love that.
And then the composition of the inverse.
Thank you. Absolutely. Let's draw a little thing out here. So we've got a point P, and that gets sent to 0 under some transformation T that we built, just like that. And then we've got our point Q that gets sent to 0 under some S. And what we want is effectively this thing here. So what we do is we first send P to 0, and then we feed it back through S inverse to get to Q. So S inverse T gets me from P to Q directly. Does that make sense? And I know that Mobius transformations are invertible. I know that these Mobius transformations form a group. so that inverses are in there and composition is always back in there. And so you just say these things. And if you have trouble like figuring out what I'm saying, let's talk. So that's two of the problems knocked out. There's some serious write-up involved. Good gobbledygook. What is problem? Did we do problem 3 already? I feel like we did. Yeah, we did that in class on Monday. Problem 3, just to quickly go through the summary of that. Problem 3 was, here's my unit circle, here's a cline, here's another cline, they don't intersect. Here's their centers. Find the fixed points of the transformation that is flip over this, then flip over this. And I think our conclusion was, I'll just share it with everybody, that if we connect the centers, the fixed points are, is that right? No, they're on the unit circle, aren't they? There you go. So these guys, that point and that point. Those are your fixed points. You move from one to the other, depending on who you flip over first. But what you need to prove, and you can argue this in lots of different ways, you need to show that those are the fixed points. So convince yourself, and you'll probably convince me, that the fixed points are where that line connecting those two intersects S1. And then we have one more problem. God, I hope we only have one more problem. Do we have 2 more problems? I'm really a bastard. Yeah, we have 2 more problems. So this one here, let me get you rolling on the horocycle one. And I have been in discussions with great minds today about this problem. I have done a lot of work on this problem on my own. So I'm not the great mind. I'm just a guy who's slugging along, getting shit knocked out. Here's S1 infinity. Here's a horocycle, H1. Here's a second horocycle, H2. Horocycles are circles that are tangent to the unit circle. So they have a point at infinity. Did you have a question, Morty?
What question is this?
Gotcha. I thought you had a question. I saw it forming, and then I kept talking. This is question 5. That wasn't assigned?
I think there was only 4 questions.
Yeah.
It was mentioned once, and then it hasn't been mentioned since.
So some of
Like
us
it's
have
not on
been
the-
spending some time on this, but I'm glad to know it's not assigned. Is that real?
Yeah, I can show
Right
you
to
the.
flip-flops?
No, that's cool. We can just say it's not assigned.
This is not-
It can be a bonus problem. Bonus work. Number 5, you want some bonus points, do number 5. It's kind of a mofo. Well then we just have to do number 6. Is that correct?
Yeah.
Number 6, I think number 6 is not that bad. I'm gonna leave you with number 6. Okay, let's work. We're not ending. Let's stay here. No one's done. Do, yes. Do. Just a reminder, next Wednesday you will meet me on the quad. You will draw geometry on the pavement with chalk that I provide, and you will get points. It'll be awesome. Bring your own jelly beans. These are mine. Good, they touched the desk. Yuck. Anybody need any consultation? Yep, yes. Is that a yes? Look at all that beautiful work.
This is like that one thing out of all my stuff. So that's. I'm just wondering if this is enough. I haven't finished this last sentence, but it's a conclusion sentence. It's just kind of.
Oh, just like, does this make sense? Is that what you want me to?
Is it enough?
Gotcha. Got the definition, I appreciate that.
So if you're in the equation on the right,
So I would say here, you could even say, instead of we will show, we know that there is. So I think we've shown it enough, we don't have to show it.
Okay.
So you can just say, we know that there is a transformation that does this, and then that'll,
be more concrete.
yeah, it'll be more concrete, and I think it's what you really are saying here, cause you're not actually showing them, you're kind of saying, you know, I've got these guys that do this, so this is great. So we'll
It's
have
in,
C1, C2.
the basics for forward sectors. I'm pretty sure that's the one I wrote down.
That's
Okay,
that makes good sense, Ella, yeah, good
Okay.
work. Yes, ma'am.
And then I sent it, did
Very nice. Yeah, you made it to class on time, I thought you might be late today or something.
We got us out a little bit early, and the church that we visited was only like a 5-minute drive from here, so it wasn't too bad. Everything else had been 20-minute drives. So it was
I'm glad
good.
you made it, so
Yeah.
thank you.
Right?
You doing good? Anything you need to chat about? You'll let me know?
And then we're
Okay.
going to a Buddhist temple
How
on
you doing?
Monday.
Good, I think.
Yeah?
Mm-hmm.
My God, what is this?
This is just logic.
Wow, that's a very organized, that's got like a flow chart and shit. It's gotta be.
That sounds.
Yeah, you don't have to show me, but wow, that's great, that's wild. That's nice. Let me know if you need anything.
Actually, can we turn off these backlights?
Oh, God, yeah, yeah, always, just let me know that anytime. Is that better?
Yes, these are the questions.
Let's just do that all around. Is that okay with everybody? I'm not diminishing anybody's, okay. Cecil, you good? You need anything? Okay. How are you doing, Morgan?
Good. I forgot my notebook, my homework notebook. So I'm looking at the photo next.
Okay, cool, okay, awesome. Camila, how you doing, friend? Doesn't it sounds like you need to prove to yourself you are.
Yeah,
Excited,
that's what I'm trying to do right
Okay,
now.
alright.
Prove to myself that I know how to start this, and
Okay.
then hopefully.
Just give it a shot and then we can still talk on Monday. Okay, or email me. We're all good. How you doing?
I think I'm struggling at connecting the definition to like making a proof of like.
The first one?
First one,
Okay,
yeah.
let's see what you got.
I just have the definition.
So I would draw some diagrams maybe. I sometimes, I think that these diagrams can be helpful in thinking about it.
Okay.
So maybe, when you look at that picture, does that,
That makes sense, yeah. I just
Yeah.
like can't, I don't know, it's not clicking with the definition, I guess.
so I would say, so draw the picture, really think about it, and then try to explain it in words. I'm gonna say draw the picture first, even though it's up there, do it with your hands.
Okay.
And then I'll check on you, yeah? Maybe it'll help the words come out. Use the word compose, that'll help.
It's just this hand, just already.
I've started.
Yeah,
But H,
This one's not terrible.
that's not all movies.
That's almost.
no, it is just the ones that map the disc back onto the disc.
It's just.
What does that mean?
So that means that, so you could take a Mobius, there are Mobius transformations that would take the disc and send it somewhere else.
For my midterm thing, she put in.
So like imagine a Mobius transformation that just scale things. Right, it takes like a unit disc and blows it up by 2, that's not part of our collection.
It has to be stuff that maintains the images.
Yeah, and in fact, everything, all of ours will look like this. So they have a very specific format, but you don't even need that format. I think you could do this proof that way, it sounds painful, cause you'll have to find the inverse formula.
Yeah.
So I don't know if I'd do that, but you could just argue, look, so if I take let's just talk about,
Would that be, so these inversions, like the Mobius transformations, would they be involved with like all inversions of basically with like circles that intersect this unit or disk at like right angles?
Yes.
Then, cause then that's the one that's maintained.
all of the ones we have are, yes, reflections over circles that intersect that orthogonally. Yes.
And then that's how we get like rotation before cycles, and like when you have like the two circles. Okay, that makes more sense.
And you could even, a lot of this argument, so like you wanted to do kind of like go think back to your original argument a long time back when you did that beautiful,
And it is.
how it's an even composition, right?
Yeah.
So if I've got some T that's in H, I know that it's equal to 2 inversions
Yeah.
over circles we just talked about. I got another one, it's equal to 2 inversions over those circles. How do you get there, the why would the composition be just?
Well, I guess I
What
can,
wouldn't? Oh, go ahead, sorry.
if I'm just trying to prove this is a group, I need to show that like
Yeah, 8.
it's closed under composition.
Yeah,
Right? I need to show that there's an identity like function in like this group of transformations, and that like any transformation has an inverse. I can like kind of skip the closed under composition.
I'm more inclined to
Like,
do it.
say like recall that any Mobius transformation is closed under composition, right? Because like these are, given that these are Mobius, like the group
Yes.
H
Yes.
are Mobius
That's true.
transformations.
And so I think then you'd have to refer to the fact that they also map D back onto D.
Yeah, that everyone in this group must have like D.
Yeah, so the composition of 2 is still a Mobius transformation, because composition, like you said, and the composition must map D on D because they each do.
Yeah.
So I think that would do it.
Yeah. I would just from there be like finding the identity transformation, and then finding the like proving the inverse.
Yeah, and what's the identity?
They might have like the small stuff that they have like at the next dance. But
Oh.
until you're older, you have a whole board.
Just remember here.
What was gonna say?
Yeah,
All of my friends are 21 and older, so they're gonna be.
I guess
I'll let you think about it. I'll let you think about that.
I can get that.
I know you can get that, actually. It's not too bad. You're gonna be alright.
Sweet. Well, thank you.
You're welcome, sir. Thank you. You're doing fine.
I think I would get, this is just a lot of explaining. You already got
True. Yeah, absolutely.
Because like, if there's math to be done, I've
There is
done
no
it.
math to be done. Our math these days is a lot of words.
Nice.
You know what
Yeah.
I mean?
I think that I have the logic down, because it's just,
That was.
Mm-hmm.
Yeah.
and
Yes.
then
Zips out.
this makes unique ones, because climb to climb, and it's to climb, to climb, to climb.
That's right.
Killer.
Correct.
Yay.
Amundo. Run to the restroom.